Okay, so we have a What the Physics video. This one is about spinning buckets of water. We just filled up, well, partially filled up little cups of water and had the handles of the cups were replaced with rubber bands so we could get a basic idea of how much tension there was as these things spun around. Just a basic thing. So we have a nice little circle on here because we were supposed to be spinning it in relatively vertical circle. It wasn't perfect by any means. That's okay. We're going to keep it nice and simple and pretend it was a nice, perfect vertical circle. Let's talk about the forces at each of the significant points on here. So let's talk about it at the bottom right here, at the tippy top, at about 3 o'clock position, and about 9 o'clock position. Okay, the first forces that we're going to be dealing with, and if you can please be writing this in on your notes, first forces that we're going to be dealing with are the easy ones. Gravitational force. Gravitational force, just find like the packet I just gave you, right? There's blank spots, okay? At the end? Okay, the gravitational force at the very bottom here, I'm going to demonstrate like this. This is F sub G. Okay, F sub G. Yeah, it is in fact recording, so this is awesome. Okay. I don't know what's going on! Gravitational force. Just get a piece of paper for right now. Okay? Thank you. These are the only contributions that some of you even make to class. You're like, oh. Okay, the gravitational force at the bottom is shown here. Why is it drawn in that direction? Because the gravitational force is downwards. Why is it drawn with that length? I don't know. I just decided to draw it with that length. What about the gravitational force up here at the tippy top, at noon position? It's also going to be down. And how is that gravitational force going to be size-wise compared to this one? It should be the same size, and it's maybe not going to be perfect, but they should be the same size. Okay? What about at the 3 o'clock position? Is it the same gravitational force? Yes, so I should draw the vector arrow to be the same. Okay, and then at the 9 o'clock position, it is the same. Okay, so these should all be the same length, close enough. Okay, that was the easy part. Gravitational force is not going to be changing based upon those slight changes in height. Now what are we going to do? I'm going to talk about the other force acting on the spinning buckets. The other force was what? The tension. Right. Okay? I will draw those in blue. First of all, let's start at the bottom again at the 6 o'clock position. What is the direction of the tension force there? Upwards. Okay? Now, how big is this going to be? Okay? I don't know right now. I'll get back to the size of the tension force shortly. But I do know it's going up at the 6 o'clock position. What about at the noon o'clock position? It's going to be going downwards. Okay? So it's going to be going downwards. What about at the 3 o'clock position? It's going to be, okay, yes, pointing to the left. Okay? And then at the 9 o'clock, 9 o'clock position, it would be pointing to the right. In other words, the tension force is always going to be pointing inwards. It's always going to be pointing inwards. Say, oh yeah, that's a centripetal force, right? Kind of. It's certainly part of the centripetal force. That's what we're going to be seeing here. Let's talk about the length again. What was one of the things that we figured out from the activity, from the spinning activity? When was it stretched out the most? At the bottom. So that would imply that the force, the tension force, was largest at the bottom, right? Okay. When was it stretched out the least? At the top. Okay. So we're doing well. So I do know that this bottom one has got to be larger than this top one. And I kind of drew it that way, but there's a little bit more to it than that. We weren't taking specific measurements, but we still can get a basic feeling for this. How will the blue arrow compare to the black arrow? As in, how will this is at the 6 o'clock position, how will the tension force compare in length to the gravitational force? Okay, there's three possibilities. They'll be the same size. Blue will be larger or blue will be smaller. Okay? So other than you say, well, I like blue, so I want blue to win. That's not really a good physics explanation. Okay? Or, hey, can't they all be the same? Can't tension and gravitational force be the same? Can't we all just get along? No, that's not a good physics explanation. What do you think and why in terms of physics? Oh, wait, I forgot what class I'm. You guys don't respond. Okay. Oh, yes, thank you. The standard. Go ahead, sir. Newton's third law of action-reaction. Okay, go ahead. What? What? They're the same. One is bigger. What? Okay, so you're saying, I'm sorry, interrupting. I think what you're trying to say is, if we are talking about, let me draw it over here, this object and the downward force here is the same size as this upward force here, that's because of Newton's third law. Is that what you're saying? Okay. Unfortunately, that is not correct. If you recall, Newton's third law is I push on you, you push back on me. Same size force and in the opposite direction, right? So yes, same size force, but these are forces on two different objects. You and I are not the same object. I am pushing on you, you push back on me. Okay, so Newton's third law, still exists, but it's not applying to what we're talking about right here. What would be more accurate is if we were trying to talk about Newton's first or second laws of inertia, and then F equals ma. What do we recall? Objects in motion stay in motion, objects at rest stay at rest. They keep doing whatever they've been doing unless they're acted upon by a net outside force. And then all of a sudden there's an acceleration. Yes? Were these things accelerating? Were they going around in a straight line? No, they're going around in a circular path. So was there acceleration? Yes, there was acceleration. What was the direction of the acceleration? What's the fancy word? Starts with a s. Okay, clockwise does not start with sound, but okay. Centripetal. Centripetal, okay? It means the acceleration and therefore the net force is going inwards. Okay, the centripetal force is going inwards. So what does that mean about the resultant force from the blue guy here and the black one there? What is the direction of the net force going to have to be? Inwards. Yes, good. Inwards. So what does that mean about the size of the blue one compared to the size of the black one? Which one is pointing inwards? The blue one. So therefore, which one has to be bigger? The blue one. Yes. Okay. Now, so let's erase this. See if I can erase it without destroying too much. But I don't need to erase the whole thing. I do need to stretch this out so it ends up being a bit larger. Okay? So there's the tension force. I don't know exactly how large it's going to be because I didn't sit there and make measurements, but I do know it has to be larger than the gravitational force. Okay, now what? Now let's talk about the top one, the one at noon. We said that's when it was stretched out the least, yeah? So what does that mean? Well, it means the tension was the smallest up there, yeah? And I said that if you can try spinning it around so it just barely makes it over the top, how much stretch was there then? If it just barely made it over the top. There was no stretch if it just barely made it over. Now, maybe you had a little stretch, you couldn't get it perfectly. Okay, that's fine. Okay? But the point is, that's where it's going to be the smallest. Okay, so I kind of already drew it the smallest. Let's see if I can shrink it down a little bit, though. And I'm not there. Okay? So that is the tension force right there. That's the tension force. It's going to be small. It could be 0 up at the highest point. Okay? But we know it's going to be small. Okay? Let's talk about the centripetal force at the different locations. Remember, this guy, the sum of the forces, we use that for the x and for the y. That just means centripetal force, yes? So centripetal force, and we're talking about for this position right here. The centripetal force at the bottom is just going to be the sum of those forces. We already said that the centripetal force at the bottom is pointing upwards, right? So we'll say that's the positive direction. So that means I'm going to say, let's see, equals tension force, and then I have to add in the gravitational force. Which way is gravitational force going? Downwards. So minus the gravitational force. So the centripetal force is the tension force minus the gravitational force. That's at the very bottom. Okay, so this is really one of the first times we've been dealing with multiple forces being the reason why something is going in a circular path. How is that going to be similar or different on top? What about what's going on up here? Okay, the centripetal force equals, well, if in this case we're saying the centripetal force is downwards, so we'll say that's positive, okay? We'll say downward is positive up at the top. Is that fine? Yeah, sure, okay. Centripetal force is saying, well, let's see. Here's the blue, that's tension. And this time we're going to add on the gravitational force. Add in the gravitational force. Because they're both in the same direction. Okay, we doing all right so far? This is why we could have 0 stretch at the very tippy top. If there's 0 stretch, that means all the centripetal force is gravitational force. You recall from the problem on the worksheet where we were saying, oh, you spin a bucket of water around in a vertical circle, and here's the length of the arm, and how fast is it going to just barely make it around? Well, that's where this is coming from. If we're saying the tension force in your arm, or in this case in the rubber band, is 0, That is the smallest acceleration it could possibly be. Okay, I don't know what you mean, Fair. What do you say? Okay, I'm saying that the centripetal force would equal the gravitational force. I said, okay, sure, I can go with that. But what does that mean? Centripetal force is mass times centripetal acceleration. So that equals mg. What do we see on both sides of the equation? M's on both sides. Guess what? They're gone. This means the centripetal acceleration is equal to little g. So the slowest it can possibly go around can be solved from here. It can be solved by saying, oh, well, a sub c, well, that's another way of saying v squared over r, and that's going to equal little g. If I solve for the r, I'm sorry, if I solve for the v, let's bring it up here. V squared equals r times little g. Okay, and then I take the square root of both sides. V equals the square root of r times little g. And if you had done that, you should have gotten the correct answer on that worksheet. Okay? Now, you say, but there, what about when we were going faster? That was so cool. Water was flying all over the place. Woo! Okay? Well, then what? Then it's no longer the gravitational force equals the centripetal force. Then it's the gravitational force adding in with the tension force equals the centripetal force. So that's why we're going faster. Okay? Now, finally, what about over here in the 3 o'clock and the 9 o'clock positions? How does the gravitational force affect things there? The circular motion there. Which way is the gravitational force going there? It's going up, down, left, right, what? They're going down. Which way is centripetal? Inwards, left or right, yes? Is down at all to the left or to the right? No. So guess what? They're perpendicular to each other. Remember that independence of perpendicular vectors thing? That's what we're talking about here. So at the 3 o'clock and the 9 o'clock position, gravity does not affect the centripetal force at all. It would only be the tension force. Now, what about if we had said, oh, what about at maybe up here, kind of a 130 position? What would be the case then? Well, I'd still have gravitational force coming down like this, okay? And then I'd also have the tension force coming in like this. What would the resultant be? The resultant would be I'd have to move my gravitational force over a little bit, adding them like vectors, and I'd get the resultant force. I didn't draw this terribly well. The resultant force would be in like this, which is supposed to be pointing toward the center of the circle. Oops. Okay, but you get the basic idea. In that case, it would once again be a combination of the gravitational and the tension. Make sense? Hopefully. Yes. Oh, good. Oh, yeah. Oh, yeah. Sure. Yeah, I'm awake. Yes. Okay. Good. All right. Delicious.